Thank you all for joining us today. I really appreciate it for kind of our inaugural Dendrite Day. My name is Harshal Goel. I'm the CEO and founder of Dendrite, and we're going to have a pretty cool agenda in store for you all. So to kick things off, we have a number of special guests. We have Greg Morris, CEO and co-founder of Vertex Manufacturing. We're going to have a small kind of fireside panel chat. Then we have Anthony Graves, who basically runs software product at HP, and followed up by Steve Walton, who's going to be giving a number of demos of kind of behind the scenes what we're doing and what we're doing with some partners. And then kind of at the end of the day, we're going to have a Q&A session where all the folks who talked today are going to come back. So please do hold your questions. We're going to do just one long Q&A kind of at the end of the day. So with that, let me make sure all my screen sharing settings are right. And let's start off the day with a fun little video we put together.
Additive manufacturing has forever changed how we design, make, and deliver things, especially those things we need the most. Unfortunately, for the technicians on the front line of this industry, the tools we use are holding us back.
These are extraordinary times, and we face an extraordinary challenge.
Dendrite provides a foundation for building new tools, tools with the power to tackle our most daunting challenges, tools that give us the freedom to think beyond the status quo, and tools that provide control over the entire process, to print reliably and repeatably. Dendrite is the new foundation for delivering solutions that weave together into a dynamic digital nervous system, a system that brings new capabilities and new scale to the digital manufacturing industry. We are only as good as the tools we use. It's time those tools got an upgrade. Dendrite, delivering the future of additive manufacturing today.
So hope you all enjoyed that video. It was actually a pretty darn good summary of what we're going to be talking about today, namely the release and development of our Voxel API, our tool pathing APIs, discussions about our relationship with HP, and then at the end, we'll announce the next event. So without further ado, it's my honor and privilege to welcome on board Greg Morris, the CEO and co-founder of Vertex Manufacturing. Greg really needs no real introduction. He is, I'd consider, one of the godfathers of metal additive manufacturing. I think a lot of us kind of depend on him and what he's done over the many years. And I, for one, I'm quite excited to hear his insights and what he has to share with us today. So with that, I'd like to bring on Greg Morris.
Well, good morning, Harshal, and good morning, maybe good afternoon for the audience that's on here. It looks like a pretty international audience, so hope everybody is managing through these unprecedented times. They are quite interesting, huh?
Yeah. I mean, you've been through all of it, right? I mean, how are these times different than maybe something that happened a decade or 2 decades or 3 decades ago? Like, are we trying?
Yeah, that ages me a little bit, but yeah, you're probably right. I was around 3 decades ago. I think what we're seeing from just a business standpoint, clearly there are many things affecting people's lives outside of business, but from a business standpoint, we've just seen swaths of industries take a huge hit. So if you're involved in the aerospace or the aviation industry, that's been pretty harsh for you this year. But across the board, I think what's also been very interesting, specific to the industry of additive, is I think probably most everybody that is on this webinar has heard the stories and read about the articles, or maybe even participated in some of the supply chain of additively produced parts to help with some of the pandemic items that were required at a very quick period of time, whether that was protective masks or some of the swabs that are being used to test for COVID. So really additive got a lot of press and some very positive press, I think, during this time. So that certainly is different than any other time in how it has really achieved center stage, I think, on the world.
So actually, you bring up a good point, right? So, I mean, when I was looking at kind of the previous set of additive and what we're looking at now, right? I mean, additive actually ended up stepping up and delivering on a few promises in an interesting way this year, right? And one of those promises could potentially be conceived as production. I mean, what's your sort of stance on the prototyping versus production side of things? You know, are we at additive production? And if not, what's holding us back?
Yeah, great question. So, I would argue that the production that we saw probably through this COVID time period and what you're referring to would more likely be centered around the polymers. So if you look at it from a material standpoint, polymers and metals being the two largest buckets, clearly, there are examples where people have leveraged these technologies to create production-oriented parts. And what does production mean? I mean, mass production could be thousands, hundreds of thousands, not probably in the millions yet. Mass customization is production on a different way. So, there are pockets. I think you can convincingly argue that additive has certainly made the jump over to the mass customization. That's been probably that for a while. And increasingly, we're seeing applications where additive is making it into the series production of multiple components of the same design. What's really, I think, very interesting, and if you look at the metals area, which is, as probably many people know, is more of my background, what we have seen is a lot of design going on that takes traditional manufacturing methodologies and combines into one component. So you have multiple parts that had a complex supply chain, and now we're combining in to make one part. Again, a story that's very familiar to people. We saw that with the fuel nozzle, the famous fuel nozzle, but we're seeing it with a lot of other components. I still would argue, though, it's a teeny tiny percentage of all parts that get produced. It's a fraction of a percent. So the future is really bright, but we're still being held back. I don't think we're quite to a point where people would sit there and say across the board that we're seeing mass production of additive components. It's changing. Medical has their examples, implants, et cetera. And we're seeing in aerospace and certain industries, this is happening, but by and large, I think we're still not at the point where I would call this production to the scale of CNC machining or castings or those type of technologies.
So you brought up, polymer specifically, right, and contrasted that with the metals, right? I mean, from my perspective, there's kind of three major aspects of additive manufacturing. There's the machines, there's the software, and then there's the materials, right? And of course, there are other aspects, but I think those three probably eat the biggest part of the pie chart, right? From just your experience, right? From starting with Morris Technologies all the way to being, at GE, right? Like, how have you seen those three things evolve over the last few years, and where do you think they need to go, right? Maybe on the machine and software side. We touched on materials.
Sure. So it's a great question. So let me kind of address each one of those maybe independently, even though they're obviously connected. From my perspective, at least, the materials have come a huge long way. When we first got involved in the industry back in 1994, a lifetime ago, but we were dealing with polymers, and the polymers at that particular moment in time were pretty fragile. I mean, you would create a part, you could drop it on the table, it would shatter into 1,000 pieces. Eventually, over time, that changed, and the polymers became pretty robust. We went from the acrylic to the epoxy polymers. Same thing with metals. When we got involved in metals, we introduced the direct metal laser sintering technology, and it was the EOS technology back in 2003. We were the first ones in North America to bring that over. That was a huge advantage for us, but the materials weren't there. I mean, we were dealing with bronze-based alloys and direct steel, and they had all they were great. They gave great detail resolution. They were worlds better than other methodologies, but they weren't really functional for a variety of reasons. They didn't have the mechanical properties and they had problems building. When we came out with the cobalt chrome, when EOS came out with that alloy, we ran that in the United States. That really changed the game. That gave us a functional alloy that could be used in gas turbine engine test beds. It could be used on medical devices, implants, or not implants, but devices and components. So it really changed the game. And now today, I would argue that we have a number of different materials, not an infinite number, but a number of highly useful materials that people are well familiar with on nickel-based alloys, titaniums, aluminum, stainless steels, carbon steels, that are, again, familiar names that they use in traditional technologies, and they work great. And they, by and large, carry with them mechanical properties that are production-like or production-oriented. So materials, I think, have come a huge way. And the machines, they too have progressed. I mean, when we first were dealing with machines, whether they were polymer or metal, they were great. They were very good and robust machines, but they were quirky. You could have these from one machine to the next, you could have issues. From one build to the next, even sometimes you could have issues. But that has improved over time, clearly, and we've come a long way. Today we have multiple modalities, and we're actually looking at multiple improvements, multiple lasers on the powder bed fusion technologies. We're starting to see the emergence of technologies like binder jet, which are very interesting and have the potential to really open up from a cost side the markets. And I would say that's probably one of the bigger stumbling blocks at the moment is the cost of components still is high. So, and the machine costs are high. So when you go from one laser to 2 to 12 or 15 or 20, your costs keep going up, and for those pieces of equipment. So very high capital costs that I think we have to address. Ultimately, the part cost is what we really have to address. And then the software, we still seem to be dealing with some of the same software problems, maybe, or I would say the software limitations that we had going back to the beginning. Now, many have been fixed. I remember back in those early days, unstitched edges, overlapping edges from the CAD systems would create immense problems when you went to create your STL file. You'd either have to correct those or you might have build crashes. So it has gotten better, but I think we're still using a lot of the same technology of the same kernels to produce our CAD software. And I think the STL file format, although it has worked, I think people recognize and believe there are probably better solutions. And moving forward, we need that flexibility. We need to be able to think about things on a mass production type of basis, whether that's mass customization or just multiple of parts that need to get serialized, and have the flexibility be able to go down to the operator. In your video, which I loved, there's a guy with a baseball bat hitting his computer keyboard, and we have to get probably the frustration there, if I guessed, is it's trying to illustrate when you have a really complex design, something maybe a heat exchanger, and the file is huge and it takes forever to go to the next step, or to have to take it into pieces to send to the additive machine. That's not what we need to see. We need to get over those hurdles, because that's not what you see in traditional manufacturing technologies. And additive needs to graduate to the level of efficiency and capability that we see in some of these other more traditional technologies.
So you brought up a good point with the CapEx cost of the machine, right? And of course, the secret here is also, if you have a large powder bed metal machine, the powder for that machine costs thousands and thousands of dollars as well per build, right? But I think one thing that's not often brought up is really the OpEx cost of the machine, right? And again, I'm not talking about the powder, I'm talking about the people running the machines themselves, trying to maintain that uptime, right? Trying to feed the machine as quickly as possible so that they can maintain that uptime. I mean, I have personally, admittedly have a pet theory about the OpEx versus CapEx costs, but I'm curious, what's your kind of opinion of the OpEx versus CapEx costs of getting into additive manufacturing? And I mean, this of course relates to where you are right now, Vertex.
Yeah, so again, I think it's very dependent, and people can probably point to both CapEx and OpEx and say, with the right application, both are viable today for a particular product. But we're not talking about specific examples. I think we're trying to talk about a broader brush solution so that people who are not just in, say, a specific industry or a specific geometry, more widespread, say automotive or many other different types of industries, would be able to say, I can both afford the equipment, so hence the CapEx, and I also have ease of use with it. So things are intuitive, and we don't have to have highly specialized individuals necessarily that have to go to the machine or have to be involved in that process. I mean, I think it's a good thing to have specialization, to have, to automate these processes, but I really think we have to keep driving that, because that's how you drive efficiency. So from my perspective, I am not the guy who has ever gone and oriented the part and put the support structures in for the powder bed fusion and gone, machined and gone over and started it per se. But, maybe I should be able to do that. Right now, I probably could not do that. But it would be nice if it was intuitive enough and repetitive enough and had the controls in place. And that's another big issue, especially in regulated industries, is you want to have the controls in place, give people the flexibility to do what they need to do in their workspace, but also have the controls enough so that you can get repeatable results out of the machine every single time. And if you don't have that, we're not going to get very far with mass production, if you will.
I think you're stealing my talking points for the next.
Sorry, not meaning to, and not trying to do a pitch here, just trying to say what I think are the.
So for those, when I repeat this exactly in the next 2 minutes, Greg and I did not talk about this before. So, I mean, on that side, right? One of the other numbers that I've been thinking about from an efficiency standpoint is sort of the ratio of operators to machines. Right? Like, how many machines can really one operator babysit, right? At a given point in time. Of course, it's very different depending on if it's a polymer machine or a metals machine. Do you have any thoughts about that ratio and where you think you want to see it going, right? Because I mean, again, if you're a machine shop, it really hits to your bottom line and affects the scale at which you can operate, right?
Yeah, so I don't know if I have necessarily an ideal number. I mean, it's clearly, if you get that ratio to be 10, 5, 10, 15 machines to one person that can operate all of those machines, the better. I mean, I think that's just obvious. So having the means and methodologies to do that's what is really the question. Is it through software? Is it through how easily the machine's architecture is to move builds in and out? Is it automation and robotics? And the answer is probably, yeah, it's probably all those things. It's probably a combination of those things. There's no silver magic bullet that's going to get one answer to everything on that list. But it really is pretty important to be able to get these machines to get the cost where it needs to be. And that's really what we're talking about, is you want to maximize the efficiency. Therefore, if you have a laser powder bed system, you want the laser to be zipping around on the surface of that build more than you want that build having to be changed out. So if you have a different type of modality, it's all about the efficiency. It's all about the productivity. How fast am I getting parts out? And frankly, if you have a $10 million machine, but it's pumping parts out incredibly fast, then you're achieving the goal, which to me is getting costs down, maintaining efficiency, and of course, also maintaining the quality of the components coming off, and making sure that, again, in regulated industries and other industries, that parts that you build today, parts that you build 3 months from now are identical, more or less.
So told we have 30 seconds left for this session. Greg, I mean, we could talk for hours, and just in a short blip, do you have anything to say about Vertex Manufacturing, plugging what you're doing now, and if anyone should contact you commercially?
Yeah, no, I appreciate that. So, we're kind of actually unique in that we're not unique per se, but we're taking advantage of traditional technologies, advanced CNC machining. We fully plan and will be incorporating robotics and automation, and as you might expect, additive, both some polymer, but also metals. And I would say that we are in an interesting period of time where I think it's been the promise of the industry for a while, but I think we're actually almost there where we should start to see a lot more applications come out leveraging additive, whether they're polymers, metals, ceramics, what have you. We just look forward to being a part of this industry again as we go forward, and appreciate the work that all companies and everybody is doing to take additive from where it is today to really that promise of mass production.
Well, again, thank you again, Greg. I really appreciate your time. I really appreciate your insights, and I wish you the best of luck in these unprecedented times.
Great. Well, thank you guys, and look forward to hearing about what's going on in the next couple of hours. Sounds exciting.
Awesome. So continuing forward, I'm going to give a brief overview of kind of what Dendrite is doing right now. We're constantly asked, what is Dendrite? Where do you guys fit, and what do you do? And so, you know, it's my goal over the next few hours to talk about what our much discussed but rarely understood technology truly does. And Al, if you're watching, I love the way you write. Please keep writing this way. It's awesome. So, what is Dendrite and where does it fit? Right, so we're constantly asked if we're a CAD company, if we make lattices or do topology optimization, or maybe, you know, do you do build prep? Are you building a tool? Are you a workflow MES tool, right? And the interesting thing here is we're actually sort of none of the above, right? I mean, if I had to really truly describe what we do, you know, this image courtesy of AMFG, you know, in this image, we're not in any actually of these buckets. I'd say that we're actually the white space. We're the thing that's connecting all of these buckets together and trying to get them to all work together in a seamless and kind of harmonious manner, right? And so, I get that seems very abstract and might not make any sense at all. And so, you know, I'm going to take some time to dive a little bit deeper into that. But yeah, if the question is what is Dendrite and where does it fit in this picture, it's literally the white space. It's the glue that holds all of it together. So before we officially get into that, you know, what is this glue trying to solve? This glue is trying to solve the handling of complex geometries. It's trying to solve the iteration time between using all of those different types of products. You know, if it takes you 10 minutes to load a file, you do that 4 times a day and have 10 folks in your company, and you know, your burn rate's $100 to $200 an hour, you've now wasted $20,000 a week just loading in files, right? That's absurd, right? Moreover, because you saw that ecosystem before, you know that we have an unnecessarily complex workflow, constantly importing and exporting between all different types of software. You'll design it in CAD, export an STL, immediately ruin it, try to fix the STL, slice it, generate some supports, bring that into the printer software, somehow connect it to your MES system and simulation system, and eventually you might actually print something, right? So to kind of echo what Greg was just saying moments ago, we're clearly wasting quite a bit of time here, but most importantly, we're actually losing the quality and the promise of additive manufacturing simply because we're constantly importing and exporting between all of these different frameworks. And so our solution is a hybrid engine. Dendrite is the maker of a core foundational engine that is capable of interacting with lots of types of geometry. You saw in the video before that, you know, we have voxels, we have distance fields, we have meshes, we have boundary representations, and quite actually much more, right? And the idea is to create an environment where all of this can work together seamlessly. The second aspect of our solution is GPU acceleration. We're heavily partnered with NVIDIA, and it's one of the reasons why some things take minutes or seconds instead of hours or days. You know, in addition to the GPU acceleration, it's a full architecture related to compute. And then finally, it's having an interface so that people can use it to enable automation and efficiency, right? So again, if you had to summarize what's Dendrite's goal and where is its place in the industry, it's the glue that connects all of it. Why does it exist? It's because we're trying to dramatically change the efficiency in the additive manufacturing industry from a time and quality standpoint. And so let's dial now even deeper. So at Dendrite, we have an engine, right? This engine is basically the thing that does all the heavy duty lifting in the background. It's doing the math, it's seeing how, things are related to each other. And most importantly, kind of in a modern context, it's doing something called compute scheduling. Basically, it is deciding whether to compute something on the CPU or the GPU, whether to compute something, on both of them, how to scale it across, a laptop, desktop, air-gapped computer, or a cloud, right? It is the key core thing that does the number crunching. And on top of this engine, a number of things can be built, right? One example thing that we're going to talk about momentarily is the HP Universal Build Manager powered by us. It's an example of a kind of a flagship application built on our engine. And I won't dive too much into it because we'll talk about it momentarily. But beyond, of course, doing build prep and build management, right? This engine can be used by a number of the machine OEMs to make customized vector and raster toolpaths. And what's the most important part of this diagram at the moment? It's the light bulbs, right? It is our mission to very directly change the power dynamic in this industry, right? Normally, when you want to go from CAD to print, somewhere along the way, someone has to give up their IP, right? And that is holding the industry back, and it's not sustainable, right? And so the idea here is, can we create a system or a framework where any machine vendor or OEM can use our engine to build plugins or build applications on top of this engine in a way that protects all of their metallurgy, polymer, and process-specific IP, right? And can we do it in a way that is agnostic to all of the processes, so that inevitably, when someone has multiple types of machines, we're not also using multiple types of software. The final part of this buildup is going well and above and expanding the machine OEM space. There are lots of types of software that we expect to be built on this engine. And to be honest, we don't even know the full extent of it, right? We have added a number of new, Dendrite Developer Council members on the MES side. We are talking to pretty much every single simulation company on the planet, and who knows where else this is going to go. But again, the key here is to provide a common framework or mode of communication, so that regardless of what type of vendor you are, we're all living in what we're going to call the Dendrite nervous system. And so who do we, Dendrite, sell to, right? And how do we, Dendrite, market ourselves? So the key folks that we interact with are machine makers. All the machines that we know today are increasing in size, increasing in precision, and there is a major data problem there, right? There has to be a way so that the machine makers don't have to reinvent the wheel or scale with the compute. They should be able to rely on a very robust mathematics library to help them with that. The second group of folks that we interface with are software companies, mostly right now on the simulation side, but we're sort of expanding there. And again, if you're doing simulation, right, the key focus there is the physics and the application, not necessarily the geometry, right? It is our goal not to necessarily tell anyone how to do anything. It is simply to be the best mathematicians in the room by being the best folks who can go and compute geometry. And then finally, the last kind of class of individuals that we deal with are on the enterprise side, right? There are a number of bespoke production and research grade solutions that really, really require that precise control, right? And there has to be a way to get out of this deadlock. And again, the key underlying theme to all of this is IP. Whether you're a machine maker, a software vendor, or a rocket or automotive enterprise user, you all have very specific IP that you want to keep precious and dear. And there has to be a way to keep advancing your solutions, remaining on the bleeding edge without revealing it, right? And so that's where we sort of fit in here, right? We're trying to provide an avenue or a glue to connect all these different pieces of software together, and then allow people to customize and make bespoke plugins or applications on top of it for their specific workflows and needs, right? So here, we just want to be the best mathematicians in the room, every room we walk into. So we've added a number of new folks to the Dendrite Developer Council, specifically AddUp, EnvisionTEC, and Link3D. I'm really excited to have even more now diversity within this council, because again, what was the purpose of this council? It was really just twofold. One, meet twice a year and have everyone yell at us and tell us what we're doing right or wrong and how we can improve, right? I think transparency is a very key tenet of our company, and we want to be transparent about what we need to fix and what we need to do to improve. And the second was to meet and genuinely talk about standards and talk about them in a way that, again, doesn't necessarily violate anyone's IP. But for example, maybe we can agree on a voxel standard for data and transmission, right? Maybe we can agree on a generic toolpathing standard that everyone can post to. Again, the key is to be very sensitive about what every single company holds dear, but do it in a way that we can actually honestly help elevate each other and really move from that prototyping to that production stage. So, I think it's probably about time we start talking about the HP Universal Build Manager powered by us. We've been, when HP came to us, they actually asked us to introduce them to a number of the Dendrite Developer Council members. So we've been talking for months now. And the goal, again, was to create an environment and fundamentally change the way this industry operates. And so, rather than necessarily stealing his thunder, I'd like to welcome and introduce Anthony Graves. He runs software product at HP, and we're going to have a brief chat about the Universal Build Manager. Anthony.
Okay, I think we're good, and I guess my camera's focusing. Thanks, Harshal. I appreciate it. I have to warn everybody that it's almost like hurricane force winds outside here in Charlotte, and I know Rachel in Raleigh is experiencing the same weather. So if I have to jump onto my hotspot real quick, bear with me. I apologize. But first and foremost, thank you, Harshal, for giving us this opportunity. It's the first opportunity that we're going to have to talk about the new HP Universal Build Manager powered by Dendrite since we announced it yesterday. And so that's exciting for us. It's a lot of hard work and effort has been going into that for months and months. And now we're finally able to reveal some of that to the industry. So we're super excited about that. And anytime you can share the stage with someone like Greg Morris, who's had the impact on the industry like he has, it's a good day. So, and I really appreciated his commentary and insights too, because a lot of us that are newer to the industry, we may have good ideas, but someone like him, when he talks, the industry listens. So I was really glad to see him here.
Well,
and looking forward to our conversation.
You have a pretty darn good background yourself, right?
Well,
Can you tell us a little bit about what you used to do before HP?
Sure. So, it's interesting. I've been in the manufacturing software industry since day one, and I can't think of a more exciting industry to work in and be a part of. And if you have an opportunity to make an impact in that industry, then it's super special. And so over the years, I worked with a number of software companies. I started a software company called HSM Works, and we ended up selling that to Autodesk. It was an integrated CAM solution for SolidWorks, ironically enough. And I was there at Autodesk and worked with that incredible team of folks in the manufacturing software group there. Then I left to co-found Fast Radius, that was focused on additive manufacturing at scale. And then I went out and started consulting for companies before I got a call from HP, just out of the blue. And when I was at HSM Works, we were partners with HP and their workstation group, the HPZ workstation group in the personal systems division, and had a phenomenal relationship with them. So when they reached out, I was intrigued. We at Fast Radius actually were one of the first customers of HP 3D printers as well. So, but they didn't call about 3D printing, they called about digital manufacturing. And it was pretty intriguing. The questions that they were asking revolved around, as they got deeper and deeper into the world of additive through 3D printing, they started to discover some gaps in technology that existed that were holding some of their customers back. And they wanted to bounce some of those questions off of me. And they were asking all the right questions. After some conversation, it became clear that they were wanting to do more than talk about these gaps, but come up with solutions to fill them. So I was eager and excited to have the opportunity to join the team and really receive a mandate to tackle some of the challenges that I believe are the key areas that are holding additive manufacturing back from becoming not only, I want to say, a first-class manufacturing citizen process, if you will, but enabling it to really achieve what everybody's been hoping for, and that's large-scale production, piggybacking off of what Greg said.
So then, I mean, so that covered kind of how you got to HP,
Yeah.
right? Fast forwarding to maybe how we met and what we've done over the last year, right? Maybe you might be best suited to explain that circus that happened.
Well, yeah, look, it's been a lot of work. When you're developing a product in particular, beyond all the other things that I do as part of Ryan Palmer's team, he is really the head of the software group. I'm not. I'm just part of that. But when we were at Formnext last year, that was the first time I had the opportunity of meeting you. HP, as you mentioned, or maybe you didn't mention, we were the first member of the Dendrite Developer Council. So your experience and relationship with HP preceded me by a number of years, preceded me joining the company. And so I had heard a lot about the technology. I was currently evaluating technologies to use so that we could create the next generation of a build management tool. We had one, it wasn't fully meeting all of our needs inside of HP, just for HP alone. And so I was given the mandate to not just create that application or recreate that application, but make one that's more universal. We'll talk about that later. But you and I met, and we had talked a little bit, and I explained it, sold one of my companies to Autodesk, and you said, what company? And I said, a CAM company. And you said, well, yeah, well, what company? And I said, HSM Works. And it turned out you used it at Berkeley in a machine shop, which is really cool. So we hit it off. And then over the next short period of time, we really talked a lot about what our goals were. And that culminated in us entering into a license agreement where we're using the Dendrite kernel as a core component to build this new build management application on top of. So we've spent many, many, many hours on the phone. Maybe many hours a day on the phone together. So it's been pretty wild.
So I think we have to at least now start talking about this build management application, right? I mean,
Yeah, sure.
One of the ways I think is maybe a good way to introduce it are the 4 pillars, right, of the manager. Could you tell us a little bit about those?
Sure. Yeah, and let me set the stage too by explaining, even though what we're going to show today, because I think we're going to give a little bit of highlight here, is going to be more of our build prep solution, build prep tool component. HP did not want us to recreate what had already been done in the industry. Now, obviously, we have to do some of that, but our focus is really on enabling scale of digital manufacturing and additive manufacturing being part of that. So we have to have build prep tools, but we really are building a build management application that goes much further beyond that. We'll talk about that a little bit later, but the 4 pillars, if you will, of our application, number 1 is universality. And I will have to tell you tell all the viewers here, when we entered into our relationship with you before we announced it publicly, we did engage with a lot of the companies that you were already working with. We inherited a lot of those relationships because we were going to be developing this front end application to really for you to showcase your technology with. And one of the things that was interesting was when we told people that we were developing a universal application, I don't think they believed this at first, but this application is universal, meaning that it is designed to support all the major additive processes from FDM to SLA, DMLS, SLS, SLA, FDM, MJF from HP and Metaljet, you name it, HSE, high-speed extrusion, et cetera. And because customers don't want to have a solution for every single process or application, that's true not only in the subtractive world with the CNC world, with CAM applications, it's true in the additive world as well. So universality is critical, and we say universal means universal. If it's a process that a large number of companies are utilizing today, we are planning to support it. And if any new processes are introduced, we'll certainly work to support those too. So that's a key pillar. The second pillar is performance. And when we talk about performance, it's a subjective term. What do we mean by that? So we inherited a lot of the performance through using your kernel. So it is It's not only GPU accelerated to leverage all of the power and capability of NVIDIA's professional graphics cards, but also CPU accelerated as well. You know, your kernel is a CPU and GPU accelerated kernel, a hybrid kernel. So we get a lot of performance out of that. And by leveraging those GPU cores, we have been able to achieve performance metrics that I think are going to really blow a lot of people out of the water when they finally get to see the solution in action. But speed for the sake of speed is not the goal. Speed in manufacturing equals agility. The more speed you have, the more agile you can be. And let me give you one real world example, because I know we don't have a ton of time, and I'm known for being able to filibuster a meeting. So let's talk about rework. Rework in manufacturing happens. You are going to damage parts. Parts are going to be out of tolerance after inspection or something. It happens in every, whether it's injection molding, CNC machining, fabrication, you have to sometimes redo jobs. And so in additive, even though the time scale when it comes to printing is much longer than in CNC and injection molding, you also have the situation where you need to be able to quickly get these builds created and funnel them into the manufacturing workflow. So performance is super critical. Flexibility is another thing. We've got it on our website. You have a case study as well. Flexibility for us, an example of that is CAD neutrality and being able to work with all of the native CAD for the most popular design tools, and also the traditional like STLs. Of course, you can't get rid of that. So the biggest thing for us is when it comes to flexibility, it's about giving customers access to all the tools that they need so that we can help them enable and scale up their workflows. And get their most out of the investment that they've made in CAD and CAM and additive technologies as well. And then the last pillar is automation. And the key to scale is, for us, is automation. And I would say it's probably one of the most important aspects of what we're doing with the Universal Build Manager, and it's this. In order for the industry to scale, in order for us to help unlock the full potential of additive manufacturing with this application, we have to give customers the tools to automate their workflows and their processes, whether it's integrating with their MES tools. And like you mentioned, AMFG, you had a quote or a diagram from them, Link3D, very popular, a new member of the DDC, whether it's integrating with MES solutions or PLM solutions, ERP solutions, or just giving customers the ability to integrate with CAD and some of their repetitive processes. Our automation is based on Python scripting, which is incredibly popular because it's easy to use, it's very powerful. And kids, even in STEM classes in elementary school, are learning that now. So those are the 4 pillars: universality, performance, flexibility, and automation. And we can talk a little bit about that later, or customers can check out the website.
So, I mean, so it seems like those 3 first pillars really tie into the automation, right? Because unless you're reading in CAD data, unless you have that speed and performance, and unless you have the universality, to me, it sort of kind of falls over, right? But again, to your point, right, speed for the sake of speed or automation for the sake of automation doesn't really mean anything.
Sure.
What does this mean from a business logic and scale standpoint, right? Like, of course, HP, likes to talk about personalization, and Ryan is a big proponent of that. But, what more, right? Like what does this actually unlock?
So, Martin Stoyer, who hopefully a lot of people know, he's been in the industry a long time, actually an alumni from Autodesk days as well, over at EOS. He has said this repetitively when he's been, when he's spoken in a number of events, including some of yours, and he's like, the whole industry has to come together and work together to build up additive manufacturing. The whole COVID pandemic, as Greg pointed out, gave people a glimpse into the potential that additive brings us, and that is the ability to scale up very quickly. But how do you scale out? That's what everybody wants to know. That's what all of the, we'll say, the industry analysts and writers, tech writers, whenever they look at additive, they're like, it's just prototyping, or yeah, it started to scale, but it hasn't reached the level where it's receiving wide adoption, where companies are starting to design for additive in mass. And the reason for that is not only the software that's driving these technologies, but it's the business models have been held back. The business models that enable scale. And when I joined HP, I said this, and Ryan's repeated this a lot, and I'm glad that he has, because it really needs to sink in. I believe the future is personalized, customized, and on demand. And if you don't believe that, I don't think you're going to be preparing for the future of manufacturing, and you're not going to be thinking about developing the tools to unlock the potential. Personalization, customization, on demand. So our focus, I'll be very clear about this, is not so much on the traditional workflows. There's tons of companies out there that have come up with good solutions for that, right? But it's enabling these high mix, high order volume business models that are those models around personalization and on demand. It's on demand replacement parts. It's on demand apparel. It's on demand consumer products, things like that, you name it. Or it could even be engineered parts for aerospace or automotive, where you have to get a part to an engineer out in the field very quickly, when a quick turnaround, and they're not on the shelf in a warehouse somewhere. So that's what we're really focused on, developing tools to allow additive to scale up. So
that's curious. So then in your mind, like once that scale up happens, right? Whether it be on the personalization, side, or like the super high end side, right? Like how do you feel additive fits into this industry as a whole, right? Because it's not going to go replace CNC machining, right? That's naive, right?
No.
Right.
Yes.
And it's also not going to necessarily replace injection molding either, right? Like there's a place where this all fits and works.
Or
right? Like,
fabrication.
how do you see additive fitting into this industry then?
Right. Well, obviously, the three reasons people, some of the reasons that people look to additive is not only being able to create parts that you couldn't create otherwise in CNC machine, injection molding, fabrication, and simplification of assemblies and stuff, but it is that personalization and on demand, those business models that can take full advantage of what additive offers. And of course, across all the different processes you have access to all these different materials that you don't have access to. And the material science. And I was talking to you about this the other day. Before additive came along, you never heard the term material science. And now you have companies that have entire departments that are dedicated to material science. And it's because whether anybody likes it or not, and this really ties back, why do we do build management and not just build prep? What is it going to take to scale additive? You have to include process development into the equation. And you can't do that if you cannot tie back all of the telemetry data and the sensor data and the materials data and all that back to the build file, then you're holding the industry back. And that's one of the biggest, when we talk to customers, and you were on a lot of these calls, that was one of their biggest complaints. They said, you know what, I have build prep, but I'm using Microsoft Excel to try and tie everything together. So forget traceability. There wasn't a good solution out there for bringing that stuff together. And that's one of the other areas that we're focused on.
So I'm seeing a bajillion questions in the Q&A chat. So FYI, we will have a longer Q&A towards the end. Just want to point that because I'm seeing them stream in.
Listen, I don't want to run out the clock here. Can you give a quick, now look, this is your show. But I did want you to have some time to be able to give a quick sneak peek of the application whenever. So
yeah, actually, well, here, why don't we do that, and then we can come back around. So here, why don't I
let's do that.
And
sure.
Show everyone a quick sneak peek. All right, can folks see my screen?
Yeah, it
Anthony,
looks great.
Cool.
Yeah.
So here we have kind of the sneak peek. We'll start by doing something relatively simple. We'll bring in a step file. Right, of course, we could bring in like a SolidWorks file or PTC Creo file or NX as well. We'll come in here and we will first start by orienting this part by selecting a surface, like so. Okay. Then we'll take this geometry, scale it up. We'll move it off the plate a bit, like so. And of course, nothing fantastic has happened so far because we just imported something. Now let's go generate a region. So what's interesting here is the Dendrite engine, it's recognizing the CAD data and it's recognizing the color metadata attached to those surfaces. And what this bubbles up to in the HPUBM is the ability to essentially automate workflows based off of this data. So for example, here, red could mean don't put supports, yellow could mean a certain type of surface finish, blue could mean a certain type of toolpathing constraint, green could be a specific type of support, right? And why is this being done? We'll pick green for now. It's being done to honestly improve the communication between the design side of the house and the manufacturing side of the house. So why don't we also come in here and just do some manual stuff that folks are used to? So come in here and select this surface. And of course, if I was using a legacy solution, I'd do this triangle nonsense, but honestly, no one on this stream has time for that. So we'll get on with our lives. We'll then come here and in HPUBM, generate some laser powder bed fusion supports. Hit apply. Don't know how well it's coming across in the stream, but this is all happening pretty much real time, right? So here we go. Then we'll do a quick 2D nest because why not? I'll then come in here and zoom in and let's see, let's just apply a little label here. And we'll call this one HP, put a number on it, hit apply. And we'll put it here and just wrap it to the surface. There you go, 0 and 1. We'll then take this and slice it at 50 microns. And again, the speed is actually nearly instantaneous here. The largest part of this is the read-write time from disk. So, we've done a basic kind of CAD to print workflow, but I think the punchline here is everyone saw me use the GUI, correct? The interesting thing is we've actually already generated all the Python and code needed to codify this entire workflow. So what does that mean? So we're going to come here and through virtue of our engine, we're going to come in here and say, save this as D-Day. And we'll come over, go to our directory where we saved it, and we'll open it up. You'll see that this was generated today on a PST time zone. We brought in the step file, we moved it around, we clicked the color green, we clicked these two surfaces, added all of these constraints to this wall support, added these tree supports, did a quick 2D nest with 2 parts. Instead of nesting 2, let's go to a production workflow and nest 25. And instead of calling this HP, let's now just call this Anthony. And instead of slicing it, I just want to see it now. So we'll just comment this out. So hopefully this was all reasonably human readable. I'll come in here and say, Python, let's go run D-Day. And we'll see exactly what just happens. So the application will launch. It'll just run through it by importing in that CAD data. It'll generate the supports using that color and surface data information. And then it'll do a quick nest at 25. I mean, it's all literally happening faster than I can speak. And you can see we have Anthony 6 right here and all the labels were changed. Right? So the beauty of this was we went from this prototyping to this production workflow with just a few button clicks. Anthony, do you want to add some commentary?
Yeah, this is perfect. And this is what the HPUBM, this is not a point application. It's a platform. We've designed it to be a platform, leveraging the capabilities of the kernel so that we can go upstream into the design and engineering phase of manufacturing all the way out to shop floor manufacturing and production through the automation with the Python scripting. So it really doesn't get easier than that. So that was great. And I'm glad you use that as an example because I think that's probably for an EOS job. I'm not sure, but, and of course, we do support HP machines, not to worry. And, but yeah, this is a list of some of the machines that we can support right now.
Good deal. So why don't
Excellent.
I do
Thanks.
one more demo and then we can maybe return to some of those questions.
Yeah, sure.
So I'll launch this guy up again.
And by the way, as you're launching that, so Harshal refers to this as the GUI version, and the application there is a GUI version application interface, but this is designed also to run headless, and it can run locally on the edge, or you'll also be able to run this in the cloud too. So it's again, when things are automated, you don't need to touch them. And the goal here is once you have a workflow that's been defined, you can capture that and then just run it infinitely. So for
Yep.
families of parts and things like that. Yeah.
So
Oh,
here,
you're gonna give that example right here. Perfect.
yep. So here I brought in a Parasolid file because why not? I'll make a quick pattern of it. Zoom in here. We'll move it up in the Z, pitch it, and rotate it a little bit to make it kind of funky. We'll just do an angular tolerance region this time. We'll then come in here and do some supports again. Again, let's just do some ones that are common to laser pattern bed fusion. All right, and here we've done kind of, again, a very simple workflow. So come here, hit save, of course, by virtue of the engine. We'll go save this as Python, right? And then what we'll do is we'll come in here and open that file up again, right? So here again, you saw this is just timestamp for right now. And now we're going to do the thing that everyone really despises. Right before you're about to hit print, of course, the design is going to change. And so in order to accommodate that design change, we're not going to redo the whole thing again. We're going to do some very advanced coding. Namely, we're going to put the number 2 in front of here for version 2. And, instead of making, a pattern of 4, why don't we do 6? Okay. So we'll come in here. We will run this file now. And of course, the thing that you want to happen is going to happen. It's going to launch the application. It's going to bring in the Parasolid file, a brand new file this time, pattern, a 6x6 pattern, and generate the supports. And again, here's where you really start to see the difference, right? You can clearly see that this geometry is different from this one, right? And it's because we didn't go through the effort of saving the specific data here, right? We went through the effort of saving a workflow and codifying it. Right. So the intention here is folks are going to be able to create rules and recipes. And that's exactly where we're seeing some of this initial kind of traction. Right. As Greg mentioned earlier, right. People need something that's reliable, repeatable, and controllable. Anthony, do you have any commentary, feedback?
No, that's great. I'm glad you kept both of those up too, so customers or customers, so viewers could see that. Yeah, it is super powerful. Python. One of the things that we'll do and we'll make available is tutorials around Python, and I'm sure we'll be offering classes too for people that haven't learned it. It's a pretty easy language to get up to speed with very quickly. So all the customers that we've talked to so far, every one of them has had people with Python scripting experience. So we've been able to do some really impressive stuff with it.
All right, well, I'm being told in my ear that we're 3 minutes over. So Anthony, again, I appreciate your time. For everyone listening on the stream, there'll be a Q&A after the next section. And again, Anthony, thank you for your time.
Yeah, thanks a lot, absolutely.
All right, so continuing on and hopefully getting back some of that time. We're gonna switch gears and talk about a number of the developments that Dendrite has been focusing on, specifically on the API development side of things. And to kind of kick things off, we're going to talk about what we've been doing in the land of voxels. And so Scott Turner graciously has provided us a video, so we'll start with that.
Hi, my name is Scott Turner. I'm the Director of Advanced Research and Development here at 3D Systems. I've been working with Dendrite for about a year as part of their developer council. And our engagement with Dendrite really started with their advanced software built on GPU technology. We believe in order to meet the needs of some of our advanced printing programs, specifically in things like regenerative medicine, bioprinting, the data sets really exceed today's technology and softwares. Our engagement with Dendrite and participation has allowed us to learn a lot about what can be done today, and we anticipate even better and larger things and data sets to be processed in the future. We also are applying this to some of our cutting edge industrial programs where we're working with data sets again that exceed today's modern CAD systems. And we see the combination of Dendrite's software kernel and APIs with really advanced GPU technology to empower real-time interaction with these data sets. And so we see it as a real benefit in our research and development here at 3D Systems.
So to touch on what Scott was just talking about here, right? We've been developing a high performance voxel API, right? And what's really the key aspect of this voxel API? So voxels in and of themselves are not necessarily a very complicated concept. You have lots of cubes, tessellating space. But the part where this starts to get very interesting is, as Scott mentioned, with these large data sets, the kinds of data sets that are actually required for scientific, engineering, and manufacturing applications, right? And so it's not enough to just have voxels. It requires more. It requires the ability to handle very large data sets. It requires the ability to enrich those data sets with extra metadata on a per voxel level. Right? Maybe you want to put RGB for coloring. Maybe you want to put some kind of thermal characteristics in there, right? Or maybe you want to put some kind of manufacturing data, related to the laser in there, and you want to use that data to drive and control this machine, right? And so the idea with what we're doing from voxels is to basically take some core technology and add and enhance it specifically for the purposes of scientific, engineering, and manufacturing applications, to really take it beyond the entertainment side and really push, the computer hardware to its limits. And so, we have a number of folks that we're working with on the voxel side of the world. We're honestly actively looking for more candidates and requirements to see how people are interested in exploring this technology. You can go to our website to learn a little bit more, but it's a lot easier to show than to tell. So why don't I just show a demo off the bat? So I'm going to come in here and show you kind of a behind the scenes look. We're going to run something called the Dendrite Voxelator, because that was just an awesome name. And what we're going to do is we're going to take something called the Stanford Dragon, which is a pretty high density mesh, and voxelize it for you live on my laptop. So I'm going to hit enter. And you can see it's already chugging. You can't probably hear my laptop fan screaming at me. But as you can see here, we've taken this mesh and we voxelized it to a pretty high resolution, right? And that's cool. That's good and dandy, right? We have all this topological data and whatnot, so that's great. But how is this useful for a manufacturing application? Well, we mentioned metadata. One type of metadata that you might want to attach to voxels are vectors, right? And one type of vector, which is really important, is the normal vector on the surface of a part, right? Because it tells us our orientation and it tells us information that might be useful for example, support generation or printing processes, right? So of course we've imbued all the voxels with that. You can see that we are showing the normal vector here because we're doing a dynamic shading on the ray trace. By the way, this is pretty much 100% running on an NVIDIA Quadro GPU at the moment, right? Then the other thing that we might want to do is take this voxel data set and apply some operations to it, right? We might want to actually take it and shell it in a robust way. We might want to intersect it with some kind of gyroid lattice. In fact, we also want to maybe attach some metadata associated to each of the different types of voxels. For example, maybe we want to look at all the voids inside the voxel. Maybe we want to take the skin off the voxel, and maybe we want to remove the shelling operation and look through just what type of data lives here, right? And again, we want to be able to seamlessly use this data, and we want to do it in a real-time capacity, right? So the frame rate on this laptop is over 30 frames per second. It's hovering between 45 and 60 frames per second, right? Then, of course, we can't stop there. We might want to dynamically slice and polygonalize these voxels. So we want to go up and down. This has all happened dynamically. None of these slices were pre-generated, from the toolpathing side, right? And we might want to take these voxels and create a signed distance field representation, right? And we might want to apply different types of chemical properties, for example, in a binder jetting process, depending on where you are within this geometry, right? Maybe so that you can pull the parts off quicker, from the supports or the setters. Maybe you want to improve a surface quality or finish. But again, we need to be able to do this on a massive scale, right? And as these machines are starting to get bigger and bigger and more sophisticated, we need to be able to handle this large data complexity and volume, right? So in other words, we need to use scale, right? So here's kind of a quick demo of what's kind of going on behind the scenes. And like I hope if you're interested by that, you'll follow up, and we'll show you some more stuff, kind of what's going on here. So to keep things moving, we'll then switch gears and push onto the tool pathing side of things. And I'll soon hand it over to Steve. So again, tool pathing is a very key component of what we need to go do. And what does tool pathing really mean? Well, it means you need to start with some CAD data or mesh data, and then you need to slice it and process it for either a vector or raster process, right? And then you need to be able to process it by either adding zones, translating it, adding offsets, adding hatching patterns at a checkerboard or micro level, with the zigzags, or you might want to apply some dithering or image post-processing. Regardless of what you want to do on a per machine basis, this is pretty sophisticated and specific to the machine. And it's Dendrite's goal and intent here to provide a core library that any machine vendor can use to push the envelope on what their machine can do, right? And the key reason that any machine vendor would want to use this is computation, like from a scale standpoint, and just so they don't have to reinvent the wheel and they can focus more on the applications and what make their machine so special, as opposed to reinventing what a wheel is or what a voxel is. So to talk a little bit more about this, I have Eve from Econity.
Dynrite brings a lot of interesting points towards our product, because first of all we are interested in is customer satisfaction. So if we have customers who are big fans of Dynrite, then of course we want to be able to provide Dynrite with our machines. Furthermore, of course, as modular as our machines are, the same approach, so to say, is used by Dynrite and the flexible Python kernel. You can basically just plug together the Python API from Dynrite to our machine. And it's similar than our modular approach with the hardware. Here we have a modular approach with the software. So that allows us, I just talked about quality assurance, that can potentially allow us to modularity or to modular change the parameters in each and every layer within the data preparation. And that's new, that has never been here.
So to keep pushing the envelope on this, I'd like to invite Steve Walton, our head of product. Steve?
Yes, thank you, Harshal. I'm going to go ahead and start sharing my screen at this point. Can you see that?
Yes.
Okay, thank you. All right, so there are 3 demos that I'm going to go through today. One, to add on to what you're just talking about on the toolpath side, we'll be giving an example of some of the hatching controls that we have. But first, I'm going to give kind of an overview of the AM process that I'm sure we are all very familiar with. I'm sure everyone has generated a similar workflow chart for AM, showing different roles between design engineers, technicians, and analysts. There may be several other roles in here as well that are not shown on this simplified diagram, and also all of these different steps. So there are many opportunities for mistakes in communication, mistakes in data entry, and also just required iterative processes. For example, maybe hatching strategies or support strategies that we see with the laser powder bed parts, for example. So this end-to-end workflow is very complicated, very multidisciplinary, as Anthony mentioned previously. And really what we're trying to do here is provide means for codifying that workflow, controlling that workflow, communicating the intent, and then automating the different operations. So demos that we'll get to here are going to be a couple we're going to break it out into 3 smaller steps. So we're going to look first kind of at the positioning, labeling, and nesting operations. And then we're going to look at the hatching and the control that we can have for the hatching operations. And then we'll look at a kind of end-to-end MES integration automation. And I think these demos are actually going to respond to some of the questions that I saw coming through in the Zoom channel about how we can interact with the printer itself. and how the scripting actually can be aware of the printer volume. Just kind of wanted to frame where we were going with these demos before we get started. And also, prior to getting started, I wanted to talk about some of the different modes of interaction we have with the Dendrite engine. So the one that you showed, Harshal, initially was this GUI interaction mode. So when using the GUI, we're accessing the engine just through this user interface using the mouse with some entry from the keyboard. We have the viewport, the object browser, and the toolbar ribbon across the top. Now the toolbar ribbon across the top very much reflects the different colored boxes on that prior chart that I just showed. And each of those boxes, in the case of the GUI, is customized. Each of those ribbon items are customized based on the machine process that we're actually using. For example, if you pick a binder jet machine, you would have different workflow items than if you had a laser powder bed machine. And some of those items at the top also include analysis and support generation. And those are opportunities for others to develop plugins to interact with the Dendrite engine. And also, as you demonstrated, through using the GUI, we are recording simple Python with each of the operations that we execute. So that is really a great way to get started with the scripting, is just recording the Python from all of the GUI interactions. They may not be the most ideal from a subsequent automation perspective, but they really kind of bootstrap that scripting process. The other mode that we have is exclusively using Python. So we can access the engine without using the GUI at all. And we can do the same operations on VREPs, STLs, CLIs, et cetera. And I'll show some of that here today. Then we have my favorite mode of operation, which is using the Python and the GUI in parallel. And so we have the GUI open. We also have Python open, and then maybe some other databases or other things like that that we'd be interacting with. And this is what I'll be primarily showing today. And then also we have the headless mode. So after we've kind of developed maybe an automation script, it can be deployed to either a local environment or the cloud to run many of these scripts in parallel to do operations on maybe multiple parts or multiple printer jobs simultaneously. So I'm gonna bring up Python here. Can you see the Python window at this point?
You might have to stop sharing your slides.
Okay, thank you very much. Okay, can you see Python here at this point now, Sarah?
Yes.
Okay, thank you very much. Okay, so what we're going to be showing again, the first one is where we're going to be looking at labeling and then a nesting demo. So labeling is something that everyone here is also familiar with. We have lots of parts on a build plate, maybe lots of coupons, and that labeling operation is pretty tedious, is error prone, and we really would prefer not to repeat that every time that we have to do a build. So in this case, what I'm going to do is I'm going to run this script and kind of describe what's happening. So this is the actually the HP UBM GUI that we're bringing up. And then we're importing some standard Python libraries after that. We're creating a printer. This is a default CLI printer, and we're loading this printer. We're then looking at a list of files in a directory. So we're searching through an entire directory here for all the files that are present. And then we're going to be loading those files one at a time. So you can see that the first file in this directory was indeed loaded. And then if we go down a little bit further, we're going to set up a sample label. So we're defining this label. We're defining the font height and depth. You can see it's also being shown here in the label dialog. After we set up this label, we actually bring up the GUI command for labeling. So now I'm going to go ahead and place this label. You can see that the label text here just says location, because the whole intent of this workflow here is just to place and record the locations of labels on parts. These may not have been labeled in the CAD tool, so we know we need to have these parts labeled for subsequent builds. So what we're going to do here is just record, again, the position of each of the labels. Okay. And then the last one in this folder, I believe, is here. Okay, so one more label to place. Select place label. Okay, so now that we have recorded the positions of all these labels, I'll hit enter. And in this case, the script at the very end is going to write out the saved locations. You can see, excuse me, you can see here. So for each of the labels that we placed, we went to the part, found the label on that part, and recorded the position. So we recorded the position and angle of these labels to a CSV file that actually was just written here. So we can quickly look at the CSV file, and we wrote for each part, the location and orientation of the label. Now, at this point, we're not going to need to hand pick the location in subsequent operations. So in another script here, what we're going to be doing is we're importing again some standard Python libraries. And then we're going to, again, open the GUI version. In this case, it wouldn't be necessary, but just to kind of demonstrate what's going on, we're going to run it this way. So again, we're going to load a similar, the same printer shown here, and then iterate through the same folder, loading the same parts. So you can see the first thing, though, I've done is I've asked the user to input the quantity of each part. Okay, so here, showing in the console down here, enter the required quantity of each part. Let's just do 3 for the first time around. Okay, so now it's going to go ahead and load the parts. After the parts are loaded, we're going to do a 2D nesting operation with all the parts that we just loaded in this directory. So here you can see the API call for actually setting up the dictionary of parts that we want to pass to the nester. So we're going to find all of the parts in the printer, and then we're going to lock the rotation with this command, and then the quantity of parts are passed here. So then we pass this dictionary of parts to the nesting operation, and that was executed, and you can see the results over here. Now, after these parts were nested, this is where we really use the information that was recorded from the label previously. So we have the positions of the labels. You can see were based on the prior position that was recorded and read from the CSV file, but the parts actually have been numbered based on their location in the build plate. So what we did here is we actually queried the printer size, so the limits of the printer, in this case, in X and Y, and we made swim lanes for binning and then sorted along X. So we have parts 1, 2, and 3 here sorted. So we could actually close this, run it again. And when we run it this time, instead of 3 parts each, we'll actually request a higher quantity of parts. Let's do 6 parts each. It'll load these parts. And I can kind of show, again, how that sorting is being done. So we actually are first dividing the printer into, again, the 10 swim lanes. And then after those swim lanes are created, we then find the bounding box of the part itself with the part limits call, and then use that information to do the sorting. So again, we have the 6 parts. They have been sorted at this point. We have the feedback here in the console window, and now the labels have been applied. So again, now we have part 1, 2, 3, 4. So this is just an example showing, a few parts that we may use, but this workflow becomes very powerful when you're recording labels for things like coupons that may be reused again and again in many, many builds. All right, so I'm gonna stop this one here and move on to the next demo that actually is going to show the operation purely in Python mode. And then this touches back on the toolpath that Harshal had mentioned previously. So this is a demo of the toolpath engine. So in this case, we're going to be only using Python. I've switched over here to this Python script. We're going to import the Dendrite toolpath library. And at the very bottom here, you see that we are going to load a CLI stack that was generated previously. This is actually a CLI stack that was based on the stator that Harshal had showed in his demo earlier today. So we have that same CLI sliced at 50 microns. And then we're going to call a couple functions here, checker 45 and plate 67. And in this case, these are just functions. I'll run this here. These are functions that are defined in this script that are just essentially setting up the call to the hatching engine. So you can see we've actually already written these two files out. So I'll open the one and show it on the right here. So what we did in the case of the checker 45, which is the one that I have open, is actually set up tile heights, macro tile heights, and width. And now these macro tiles, actually the way they're set up in this are making a checkerboard pattern. So we are tiling or tessellating the entire part with this checkerboard, defining the hatch spacing and hatch length, number of contours that are going to be around the perimeter of the part, and the contour spacing. Then we are going to be rotating the hatches from tile to tile at 45 degrees and 30 degrees layer to layer. So now that I've described that, I'm going to center the view here and step up through layers one at a time, or in this case, we'll make some larger steps and zoom in and kind of show the detail of what's going on here between the different tiles. So here you can see if we go from, you see this is a simple layer to look at with horizontal and 45-degree angle hatches. Zooming in, you can see that we asked for 0 overlap. So this is where the interior hatches are becoming adjacent or coincident with the inner contour here. That's just one sample of how we can control the hatches. So if I open the other file that we generated at the same time, which is plate 67, here we have the same CLI stack. We just generated hatches using a different strategy at the same time. So I'll step up to a similar height that we were just looking at. And you can see that in this case, what we did is we requested really just stripes. So we made stripes across the entire build plate. You don't see the checkerboard in this case at all. We have a hatch spacing of 100 microns, a hatch length of 7 millimeters, and we've actually requested 5 contours in this case. You can see there are areas that are not thick enough on this geometry to receive 5 contours. So in some cases, we have only written 3 out. And there are other areas where you can indeed, you have enough geometry thickness to actually accept the 5 contours, and those have all been written here. And also, it's just nice to point out the offset. We have 50 microns between the interior hatches and the contours. So one other strategy that I like to show that we've added more recently and plan to extend to arbitrary geometries is actually the tessellation of a hex pattern. So I'm going to comment those first 2 functions out here and add the, and actually run the hex 45 function. Run that one more time. And I'll go and actually show that function definition here. Again, we're defining the tile height, the tile width, hatch spacing of 100 microns, hatch length of 1 millimeter, 3 contours, and some other configurations. So this one, okay, has finished. It's now available to view over here in this folder. You can scroll up through all of these layers. And here we can zoom in and see, in this case, we configured the rotation to be 30 degrees per layer, and also configured the overlap to be 100 microns, which is the entire width of the contour. So in this case, the hatches are going to the exterior of the part along with the contour. So this is just a demonstration of some of the ability to control each of the different hatching strategies. One example of the ability to tessellate the part to further control the hatching on a per layer basis. Okay, so now I'm going to move to the last demo. This one is more of an end-to-end demo where we're going to be showing integration with a hypothetical MES system. So in this case, let me actually load the database or show the database that we're going to be working with. I'm going to start this in the background and we'll start running this. So this demo actually loads data out of a mock MES database where we have customer orders information. So we have a customer or an order. There are certain file names associated with that customer. We may have a due date associated with the customer. And we might want some other report information like build ID, pack time, things like that in the end. We might have a more operation-centric view where we are looking at a table of builds. So in this case, we have a build ID. We might want to know what customers are actually associated with that build after it's been completed. And we want to know how many parts are in there, how long it took to do the nesting operation. In this case, we're doing HP 3D nesting operation. And then we want to have a report of the packing density. So you can see we actually finished the first iteration and the data was written back to the database in this case, along with the build file, the JSON build file for the Dendrite engine. And so in addition, in this final report, we have a report just on the computer information. This is a report from my computer that I'm using to run this demo right now. So if I describe what's happening in the Python file, we first import several standard Python libraries. We also import the Airtable API, which is actually the web-based database that I'm using to interact with and record this information. So we look up some of the base information, the table information, and first thing we do is actually see if we have an open build. So we query to see if we have an open build. And if we do, we move on and start querying the rest of the customer and file information using the more complex script in this demo, where we import a few other libraries. And also in this script, we set up some initial parameters for our completely automated build scheduling tool here. We have some a concept of due date, which we'll use for when things are, we'll sort by this or whether or not they're past due. We also will have a threshold of density limit. And so for the purposes of this demo, I just set it to be 1%. And so when this build is at 1% fully nested or 1% packing density, it'll close the build, save the file. So we load in through the Python and Airtable APIs, the data from these different tables. We first sort by part count. So we want to start with nesting orders from customers that have lots of parts in them, just the logic that I chose to use here. We then also sort to prioritize customers that are late or due within the next 10 days. And from that sorting, we end up with two different lists. And we pass those lists to this function that we have defined. And within that function, this is where we actually add the parts to the job. And we add the parts to the job. We iterate over these lists. We create the part here. And then we also insert the part into the center of the build volume. And after that's been done, we do this for all of the parts that we're going to add in that one operation. And then we build the dictionary of default parts to send to the 3D nester. We send that to the 3D nester here with this call, along with the other nesting configuration items like spacing margin, how many cycles we're going to run the nester for, whether or not we're going to use these other strategies for looking at thermal aura for the HP process, or look at large part priority, which enables a more optimal solution when you're looking at parts that have very large differences in part size. And then when that's done, we calculate the duration of that operation to send back to the final report, and then also query the printer volume and the part volume to calculate the packing density. And here you can see this is the API call to the printer limits. So we're finding the different corners of the printer volume and then, or of the printer, and then just calculating the volume from that. And then for each of the parts, we're querying the parts, the part geometry to find the volume. And then we're summing that, that volume to find the total part volume, and then just divide by the printer volume for the final report. One other thing that we talked about, and this touches back to what Anthony was talking about earlier, is we actually, there is a lot of uncertainty in the process today, and there is rework that's involved. And so we are also providing in the report for each part where the part is located in the build and what the maximum Z height of the part is. So those queries are done here. So we're actually finding the limits of the part in each direction and finding the center of the part and reporting it here. And then also finding the maximum height of the part using this API call and reporting it here. So if we have a build stoppage or build failure, that can be automatic, that'll be reported back along with any parts that are maybe above that threshold that are gonna need to be either evaluated, reworked, reprinted, et cetera. So as you can see, while I was talking here, this actually met the 1% threshold and wrote back to the database that this is indeed done. We have this list of customers here that was written back. And then the rest of the report on a build basis would be right here. So what I've just gone through again is 3 demos showing more in more detail about the Python interaction specifically in this mode with Python and the GUI, and with some other tools up as well. Again, this is my preferred mode right now for workflow development. And further, there's even more interactive mode when you're actually using in Python in debugger mode. And I know one thing to add here, Harshal likes to point out that I have no formal software background and really started using Python for the first time in the last 6 months. So most of this is, the whole applications team has limited software experience. And so don't be too critical, but we are showing great examples of how you can learn to use Python and try to provide some of the tools for kind of the interactive learning through the GUI Python script recording, and then also debugger mode with Python. So I think prior to the Q&A session, I'm going to hand this back to Harshal.
Thank you, Steve. So I know I have a feeling this Q&A is going to go long, so I'll just do a quick summary, talk about some future stuff, and we'll get right to the Q&A. So in summary, today you saw, the Voxel API developments that we're doing, the toolpathing API developments we're doing, the developments with HP around their product, the HP Universal Build Manager powered by Dendrite. If you are a machine vendor, a software technology provider, or just someone who is an advanced user, please do ping us and contact us. Our website was recently updated, and you're more than welcome to ping us through any of those channels. The other thing I want to mention is, due to some great demand, we're going to be hosting another Investor Day for startups. This day is going to be January 19th. We've already assembled a panel of some pretty darn awesome luminaries. We have Amar Hansbal, the CEO of Bright Machines, and had a product over at Autodesk previously. We have Avinash Raghuboor from Rival. We have Ron Fritz, who's the CEO of TechSoft 3D. We have Heidi Roizen, who is Threshold Ventures. And of course, we have James Taylor returning. So with that, I'd like to bring back the key guests, Greg and Anthony, and we'll open it up for Q&A. I believe we're going to be slowly walking through the questions that have been already asked to date. And I believe some of the press are also going to be allowed to raise their hand to ask more questions. So with that, Greg and Anthony.
So I'm going to be asking the questions for all of you. I want to say thank you to everybody for all of the questions. We got a lot. And I'm going to start with a simple one for Anthony, which is, we've had a number of these questions. What's the availability of HP UBM? When can we try it? When can we download it? And so on, if you would like to explain that.
Okay, so we're planning to do a winter beta sometime around the February timeframe. That's our target right now. And then with a spring launch, an official launch. So what we've done right now is we've just made an announcement. We are working with some pilot or lighthouse accounts across all of the industries. And if any viewer thinks that you have a really unique or challenging scenario that you'd like us to talk with you about, we can certainly do that. But our bandwidth is a little bit limited. So they can reach out to us. There is a contact button on, I think I'll give you 2 URLs. One of them is off of Dendrite, which is dendrite.com/UBM. And then we have one as well. The short version is bit.ly/capital HP-capital UBM. And then either way, you can sign up to contact us there. So that's the short version.
All right, perfect. There's another one for Anthony. What type of feedback have you received from the other OEMs in the industry that you have engaged with?
Yeah, and we did list them in our announcement. I apologize for not mentioning them earlier. But we've talked extensively with a lot of the OEMs, SLM, Renishaw, EOS, Econity, Aon, who you saw earlier, Plural, Aurora, and there's many. And again, I've listed them all out, Impossible Objects and others. I'll tell you, the feedback was universally very positive. And we knew we were onto something when we started contacting these folks 6 months ago, and let them know in those initial phone calls that we were planning to do this, and that we had a plug-in architecture. We were eager to work with them to see how we could best support their customers and their printers and their processes. And that did not leak. And when you have 16 or 18 companies that all know something, like HP is going to do a Universal Build Manager application, and it doesn't leak, I think that says something. So I was shocked. I've spoken to a lot of people in the press, and they said they've never seen that. So it was overwhelmingly positive. And so we're excited about that.
All right, perfect. This one's from John Callan, and it's for Anthony or Harshal, both of you.
Cool.
I hope John's still here. He says, UBM looks interesting. Are there tools that actually analyze the part geometry to optimize part orientation or optimize supports? Second part of the question, does the system support higher order geometry like splines rather than linear vectors? So over to you both.
Harshal, I'll let you lead off.
The minute we start with higher order splines instead of vectors. So the answer to that is yes, we bring in the native CAD geometry, so the standard spline data. I also saw another question, whether or not we do conversions or whatnot. The idea here is to not convert anything. So if you bring something in that's considered the ground truth of data, right? And before any conversion or anything is done, some major steps have to take place. On the other side of things, the idea here is to make it so that you can use the existing orientation optimization or support generation strategies that exist in our engine. I'm sure HP is going to make more themselves. You can make your own as well. And quite honestly, any other machine vendor or ISV can make them too, right? I'll repeat that it's not our intention to tell anyone how to do their job or how, or what to do. It's to simply create an opportunity for anyone to innovate and create bespoke things for their process and solution. Anthony, do you have to add?
Yeah, the only thing I was going to add on that was, HP, we created our first plugin for our application using our 3D Nester that we developed in-house. That was a thermally aware MJF focused Nester. And there's a lot of flexibility, and that's one of the neat things, like you mentioned, with the plugin architecture. Any of our OEM partners can develop enhancements that specifically address unique capabilities for their printers. Like the angle is huge in some processes. The part angle as it's being built. So they can develop that, protect their own IP, but it's compatible. If it's built on top of the Dendrite kernel, then there's instant compatibility with our application, which is a really nice benefit of using the kernel.
Okay, you both done? All right. Yep. We're going to jump around a bit here. There's lots of really interesting questions running across the entire topics today. Got one here from Quinn Muntal for Harshal. Is the Python SDK just a wrapper over a usable C API? And to explain, for basic workflows, Python is really handy, but once one starts developing complex plugins, moving to a static type language is a no-brainer, even more taking into account that an error in the script will cost machine time and money.
Yeah, of course. So yeah, under the underlying architecture, our code base, like the Dendrite engine code base, is in C++ and NVIDIA CUDA, right? And of course, there's a Python binding system that's put on top of that as well. We are working on a C API shim layer to make the interaction with the engine a lot nicer and simpler to work with. Of course, there's a lot of surface area, so we're going through and prioritizing what aspects of the C shim API we expose. But yes, that is the intended mode of connection and operation, whether you're building your own standalone application or trying to build a plugin for another application, right? And the Python is meant to be a way to potentially just accelerate that development process, just because it's so much easier to write it quickly.
Okay, next question. This is from an anonymous attendee. Is the voxel an extension of the NVIDIA GPU voxel framework, or is it written from scratch? What is the voxel resolution supported for you, Harshal?
Good question. So I'll start with the resolution. So we are seeing things anywhere from like 600 to 1200 DPI on like a 1 meter bed size, right? We've been seeing, and we've only been seeing that precision go up. So I think it's not a question of what's supported, it's what are we trying to support on what timeline, right? And the answer is trying to support people as quickly as humanly possible. The second aspect of this is, yep, so there's a lot of voxel libraries out there. I think given the amount of work that we've done at this point, it would be more fair to not call it a descendant, but like a distant cousin, just because of the amount of work and effort we've put to make these existing, for example, NVIDIA or Intel CPU libraries much more robust, but B, how we have modified them to really handle these manufacturing use cases and scientific use cases. So yes, there's definitely some inspiration coming from some of the NVIDIA libraries, but this has, quite honestly, at some point, I think it's just our library now, given the amount of rewrite.
Okay. Got a question here from Sarah Gurkey at Fabaloo. Hi, Sarah. Thank you for asking the question. She says, from an experiential sense, how has the process of industry collaboration gone in bringing these solutions to 3D printer OEMs and partners? And I think this is a lot for Anthony. What has the workflow been like, and how can we expect to see collaborations continue? Anthony, maybe you start, and Harshal, you follow up.
Yeah, well, I'll just tell you that all the heavy lifting was done by Dendrite, period. Like I said, when we started working with Dendrite, as part of the Dendrite Developer Council, those relationships began to develop, but through the work of Dendrite working with the OEMs, when we started working with Dendrite and building on top of the kernel, like I said, all those introductions were made at a much higher or lower level, depending upon how you look at it. And so I should probably let Harshal complete the thought there, because he did most of the work.
So I think we were both in every meeting, all right? And, every meeting had some level of consternation, of course, right? Because this is a major departure, right? Like, at least in the additive industry, a number of folks are very egocentric, like self-centric. So I'd say there's a spectrum, right? There are some folks, on the startup side who are just like, oh my God, I need to figure out a way to get this done. Please help me as soon as possible, right? Like, this is a major burden off me, right? Then all the way to the side of the spectrum of, okay, this is interesting, but we have our own solutions and roadmap. We need to really discuss how this fits and how this all works from an IP and monetary standpoint, right? So, are we done? No. But to Anthony's point earlier, I think, across the board, we were genuinely pleased and surprised at how receptive everyone was across the board, because I think folks realize that we have to work together to make this industry kind of elevate, right? And I mean, case in point, even in the HP press release that came out, right? Most people may have been surprised to see X1 on there. Well, I'm sure they were also surprised the first time we rang them up, but it's to prove a point, right? Like, universal does mean universal, and we have to work together to help each other, right? At least on the software side.
Yeah, I'll just add one thing real quick. One of the biggest things that struck me when I got into this side of the business was at how, frankly, a lot of the issues you had around competition that existed 20, 30 years ago in the CNC world, the CAD/CAM world, were just starting to percolate to the top in additive, where it used to be everybody thought their machine, their CNC, was the only machine that could cut metal or wood or plastic. And it's like, that's ridiculous. And it becomes even more ridiculous when you look at additive, because the processes in most cases are so different and approaches across processes are so different. I think everybody needs to take the attitude we certainly have, and Dyndrite has. The customers are smart enough to figure out what they need to buy from a manufacturing standpoint. It's our responsibility to create great tools and let the customers in the market decide who's best in what scenario. And whether anybody likes it or not, that's what the market's going to do. So I have been super impressed by a lot of the OEMs, because they also have that attitude inside of additive, or the 3D printer manufacturers. They were eager to talk with us, and so that was great. I was pleasantly surprised by that. So that was great.
I'll ask Greg a question. Greg, have you ever accidentally bought an EOS machine when you needed a CNC machine, or accidentally bought a GE machine when you needed a polymer machine? Have you ever accidentally made a multi-million-dollar error like that?
Yeah, well, no, and if I did, I should be fired, right?
Right.
Okay. I have another question, and this is for Greg. Hi, Greg. This is something you answered online a little earlier, but most of the attendees don't get to see the question or your response. And so I'm just going to try it again here. All right. So do you think the problem with comparing AM to traditional production options is that AM is not locked down for one operation? You need to validate the process each time you throw something new at the AM system, right? Would you like to comment?
Sure. So I think if I understood the question, and you're right, I did answer that. But if I understood the question, I think you find that even in traditional manufacturing methodologies. And the example I gave was, if you're in the middle of milling something and you need to put in a new end mill, let's say your end mill broke or what have you, you're introducing a variable there. So it's not exclusively in the domain of additive. It is a problem, and clearly additive has a lot of moving pieces around it that you have to be cognizant of. But traditional manufacturing methodologies overcome that with processes and understanding where those variables can come in. And the same thing goes for additive. You have to lock down your machine. You have to understand your upper and lower limits. You have to know all, as I mentioned in my reply previously on that, was the buttons, the knobs, the levers. Understand all of that, control all of that, and then if you have that under control and you have gone through a rigorous set of testing to be sure that you get build to build the same components, that answers the question of, can you throw in different geometries into that same material, if you will. If you change something, you have to go through a process that should be well understood as to, like, for instance, a laser swap and a laser powder bed. You need to go through that testing process. It doesn't mean you have to go start from the beginning. It just means you have to go back to baseline and say, okay, am I meeting the mechanicals and chemicals and the tolerancing that I need to meet? So it is doable. It can be daunting. It depends on the modality. It depends on many different factors. But clearly it is fully, one is fully able to lock those things down, monitor it, and especially in highly regulated industries like aviation, medical, and others, it is entirely possible to have consistency of product, even different geometries going in there from one machine. You just have to continue to do that for each new machine that comes in, even the same model and everything else. You have to just go through that process typically.
All right, thank you. Anybody got anything to add to that?
Yeah, Greg's 100% right. You have to validate all manufacturing processes, regardless of whether it's CNC or additive. That's just the nature of manufacturing. So no difference here.
All right, perfect. Okay, I've got a question here from Matthew Duffy. Thank you, Matthew. And this is for Harshil and Steve, right? You two can figure it out. Question, with the toolpath generation tools, are you able to apply borders, contours, downskin, etc., based on features or surfaces? An example that comes to mind is wanting to apply borders to internal channels, but not the outer surface of the part because it will be machined off.
I'll let Steve handle that because we've been discussing that for months now.
Yeah, sure. Thanks, Harshal. So the ability to identify different regions based on overhang, like upskin, downskin angle is something that is fairly imminent actually in the toolpathing API. So that will be something that's coming very soon. I'm interested in the workflow about offsetting specific areas. So that's something that actually would probably work really well through the color workflow, right? You can identify surfaces like the inside of channels, for example, that you would not want to be additionally offset. So that color metadata that could be read in through the native CAD file would be able to be passed to the toolpath engine to be able to do those offsetting on the fly. I think that's a great additional use case that I don't see any reason that we will not be able to support that in the future. That's a great application.
Yeah, the only thing I'd add is whoever asked the question, please do reach out. We'd love to talk to you more about these kinds of things. We're actively soliciting feedback and advice on Toolpath API and development.
Yep, thanks.
Okay, next question from Doug Dingus at Plural. Hi, Doug. So he goes, with regards to the, excuse me, the Voxel API, will we see the ability to combine a voxel map with a traditional CAD model to define things like material regions?
I think that's sort of just inevitable, right? And that's where it's going. I think maybe some of the initial materials might be color oriented, or maybe they're oriented based off of like a stress field that comes out of, a simulation package made by either like ANSYS, Altair, or Hexagon. But if it's not there today, I 100% believe that that's the direction that this is going.
Okay, perfect. Yeah, another question from Adam Penner, who runs the awesome Additive Manufacturing podcast. Very quick question. Is closed loop melt pool monitoring next?
I think we have a lot of problems to go solve right now, but doing some kind of in situ process monitoring and control, so the engine can be run in a headless environment, even on the machine itself, right? So I do believe that that is going to be happening at some point, but at least in the immediate term future, that's not the prime focus. But that is, I do believe, where this is heading, just because of the nature of our engine as a whole. Anthony, do you have commentary?
I mean, this is what we were talking about when we talk about build management. This additive is closed loop. You cannot operate without monitoring and managing the data of the actual parts being produced, because in many cases, particularly when we talk about personalization on demand, you can't SPC orders of one, right? There aren't 30 or 60 or 150 parts. So you really need to nail that process down, and you have to be able to monitor things other than the part on the fly, just as one use case, for example. So yeah, it has to be addressed eventually. So.
Okay.
Yeah.
Question for Steve from Sean. How does Dyndrite address machine variability in additive?
So I think this ties into a little bit about what Greg was saying, and maybe Greg, do you want to define machine variability? I feel like you have a lot of experience with that.
Yeah, well, look, I think you get machine variability even with quote unquote identical machines. But again, back to traditional manufacturing, no different, right? I mean, it's you'll get the same thing, the same variability in CNC machines, machine to machine. But in additive, it seems to be maybe sometimes a little more pronounced. And so even though they are identical, you will have differences in output from one machine to the next. And there are don't have enough time to go into the myriad of reasons why that potentially is, but it is a fact. Sometimes it's dramatic, sometimes it's very nuanced, but regardless, you have to anticipate you will have some differences from one machine to the next, even though they are identical in the same facility, in the same atmosphere. That can happen and oftentimes will happen.
By the way,
assuming.
An important point, really important point. I just want to piggyback off of real quick. This is huge. And it's like, if you think in CNC, in the CNC world, you modify your post processor for different types of machines. You could have, for example, 5 Haas CNCs that were all produced within 2 months of each other. And you have to maybe tweak the post processor just a little bit in some cases. And maybe that's a little bit exaggerated, but it's not uncommon. In additive, that's sort of the beauty of the automation. You can lock down, it's not just the output, modifying the output, but it's how you deal with the data as you're creating the build file. Super important, because you can create these builds for specific machines, not just routing, to get around the fact that there is, in some cases, an increased or more pronounced, I think you said, Greg, level of variability across machines from machine to machine in additive. So this is one way we're planning to help customers address that fact. So.
Yeah, the only thing I'd have to add to that is, we've talked a little bit about creating recipes, last couple of hours, right? So you can create recipes for part families, for labeling and whatnot and support generation. But to be honest, you should be able to also create recipes on a per machine basis within your factory floor environment. Steve?
Yeah, so we're currently already have the ability to save machine configurations, save various tensile test specimen configurations, keep out zones, other build prep aids on the printer side that can be saved in one, that's one concept. The other is the save configuration for a build, like as prepared, is something that you could start from and reload for a specific machine as a starting point, and that could be a save configuration you load in and bring in your parts automatically into, and do a lot of the front end tedious work in configuring that environment prior to handing it to the operator to provide the real value added operations.
All right, thank you. Question from Kai Zhang. Does UBM use a universal build file format to interface with different OEM systems? If yes, what is that file format? Or is there any plan to standardize it? And if not, how does UBM handle various OEM file formats?
So I can answer that question, probably because I have a bias. So let's just say we are trying to create some standards here, in the manufacturing land, right? And to be honest, I'm trying to create those standards at the lowest level possible so that they can be agnostic on a per machine basis, right? So we're going to be announcing, for example, support for EOS job files, right, today, right? But the idea is you should be able to create a Renisha MPT file or a .slm file pretty darn simply from some base level ground truth. Right, so this is an active discussion among all of the DDC council members, and let's hope that can happen relatively soon. We have some proposals, and we're going to create a working group around it.
Yeah, that's yeah.
Okay, we're right at the top of the hour, and I think that we've answered most questions either during the demos or during this Q&A. Harshal, is there any other questions that you spotted that you felt need to be answered?
Yeah. So let me just kind of machine gun through all the questions on my Q&A dialogue, all right? Do you guys support implicit modeling? We have all types of modeling. Do you modify the part geometry in the build manager or the kernel, and how is this data sent back to the CAD or PLM system? No, none of that is modified. In fact, you can hopefully save that the JSON or the Python file configurations and push that into the PLM system. Voxel API, can the properties be connected to the voxel, such as print parameters? Yep, that's the intent that this is going. Let's see, is G-code generation supported? Not immediately at the moment, but that's also the direction that this is going. We're working with a number of FDM folks to hopefully support Mach, Marlin, and FANUC G-code. Let's see, tool by generation tools, automate, labeling. With the labeling function, will the toolpaths need to be regenerated every single time? So the way that our engine handles labeling, we don't actually merge anything in 3D. We actually dynamically merge things at the 2D slice level, right? So you don't necessarily need to reslice the whole build every single time or necessarily regenerate all of the toolpaths the whole time. You obviously need to regenerate the toolpath for that specific label, but the idea is that you can merge that in, right? And so maybe you can, lock a configuration of a build of a bunch of medical device parts and do some dynamic merging, so you don't have to necessarily requalify all of them because the labels are so small anyway. Let's see, what else? Some questions around, do you support 3MF and does this include color? So unfortunately, we have to create the 3MF files for the HP machine. The fact that I said the word unfortunately means that I have opinions. You'll see those opinions come out in the press and media relatively soon. Does Dendrite preserve geometry, monitoring? So can you snap label placements to edge points and reference points? So right now, all of the labeling is done based off of a coordinate and a normal vector, but the idea to do some geometric recognition, not only for support generation, but placements and patterning, that is expected to be added to the engine over the next year or so. Do you support importing CLI slice files? Yep, Steve just showed that during the demo today. What types of input files do you support? So the engine supports natively all of the major CAD formats. And we also support STL. Does Dendrite do generative design, and is that planned? Honestly, this is also one of my trigger words. I don't really understand what on God's green earth generative design is. I think it's become a fad. So because I don't understand what it means, and because it's been diluted, I'm going to say no. That being said, it is our goal to help people for what I think generative design should be. And to answer the simulation side of this, Dendrite is not interested in doing any physics or simulation. We simply want to handle the geometry. We're leaving all the simulation and physics to the other multi-billion-dollar companies in the space. There's already a huge ocean to boil. Are there any plans to support WebGL? Not really at the moment. There are some ideas that we have kind of floating around, but we're primarily focused on the performance and speed of the engine, and we've built a very custom render engine to support that. And so, headless things can happen in the cloud, but on a, this is also set up for visualization on a local machine. And then I see another question from Kai Zhang, follow-up question. What's your workflow to support the EOS job file, since the EOS machine needs connection in general? So the idea here with the EOS job file is, it's a pretty straightforward format. It is mixed up of a bunch of the CLI data, printer specifications, and some material parameter stuff. So it turns out that you don't necessarily need to fully connect to the machine to necessarily get all of it. We can, for example, take an entire build, generate all the slices, do all the segmenting and zoning. You can then generate the job. You can then bring it into, for example, software that connects to the machine and do some final exposure strategy stuff and send it to the machine. We are going to be working with a number of folks to get that final mile. But at the moment, when we do the EOS job, we're essentially just prepping everything up except the final exposure strategy step. So I know that was pretty fast, but I just ran through 25 questions.
Oh, that's great. I got one final question. I actually think it's a little important. And this is for Anthony first, maybe Harshal, you as follow-up. How does the HP announcement impact HP's relationship with their partners?
Great question. Whoever asked. I guess, look, let's be honest about this in two respects. First, for us, build prep is a part of our solution. It's part of build management. It's really, for us, it's table stakes to get into this world. So there are going to be cases based on our speed, our performance, our flexibility, et cetera, where people are going to take a look based on their application, whether they have very complex files, very large files that take a super long amount of time to slice today, things like that, with the existing applications. And they're going to look at our application and maybe it's going to provide some real benefits for them, right? But we are not arrogant or naive enough to think that we're going to come into this market and immediately produce a category killer. That isn't even our objective. Our objective is creating an entirely new category, to be honest with you. As I mentioned early on, my mandate wasn't to come out here and replicate what existed. from anyone, let alone our partners. And we have awesome partners. Siemens is one of our biggest partners inside of HP. There's Siemens NX, it's phenomenal. Materialize is the industry leader by market size, market share. Autodesk, my alma mater, not only with NetFab, but Fusion. Fusion's a really good example because they're sort of targeting a certain type of customer like we are with the HP Universal Build Manager. I think you could look at it as the two bookends, right? And so for us and our focus on high mix, high order volume, these new markets, personalization and on demand, is and our build management aspect of capturing all of the data sets involved in the production process is different. And so we're going after different customers. And the reality is, and I think Greg probably, if anyone could ever speak to this truth, companies don't invest in a product. They invest in a solution. And companies that have invested in existing solutions have spent an incredible amount of time and effort, not just cost on the solution itself, but developing processes around those solutions. As Greg mentioned on validation, you don't validate an entire plant and then take a major component and just throw it out. It takes, in some cases, 12, 18, 24, 36 months to do something like that. A lot of planning is required, even for small companies, if they're in regulated markets. So realistically, I know in some cases, it probably came as a shock to some of the people at some of our partners. Some of our partners knew about it. And let's just say we've had some conversations, but at the end of the day, I'm going to go all the way back to what I said at the beginning and the comment that Martin Stoyer said many times. Martin, as a member of the DDC, which I think is an indication how people, I think, have a healthy and mature, at least in the OEM world and the ISV world, perspective about what is it, cooperation or something, I forget the term. But I think that us entering this market is going to open opportunities for everyone. I know it will, including our partners. And there will be opportunities for us to license our technology to people. We can license technology for our solution. I don't think it's going to be unheard of to see some of our partners creating plugins for our platform, to be quite honest with you. And our solution being used headlessly to support things like Siemens MES applications. So it'll be a little bit of a blip, but at the end of the day, I think it's going to be positive for everybody involved. That's certainly our belief. And so I think that's the best I can answer that question. Harshal, anything else? Or
I think that covers it, right?
From your perspective,
I think the key here is it's this optionality, right? Like I don't think we Dendrite are saying that we are the best at doing like MES simulation or anything, right? Even for example, Steve's demo today, right, connecting to a database. It wasn't a demo saying we're going into MES workflow applications. We have no interest in that, right? We have an interest in enabling and elevating everyone across the board, right? And if folks do better nesting than us, like for example, for an HP machine, more props to them. If they do better support generation than us for an EOS SLM machine, more props to them, right? Like if they come up with a better way to define supports to minimize deformation because they did all this fantastic simulation analysis, more props to them, right? The key here, again, to go back to it is to be that glue that brings folks together so that this kind of weird segmented world doesn't exist anymore. And again, give them back that control over that IP, right? And again, it all goes back to that IP. Who owns what? Why are they doing it? And from a business standpoint, it's kind of like the key thing, right? It's if we can enable people, lots of people, to make money off of this, the market's going to decide who wants what and how it needs to be set up. Right, like it's the key is the optionality, and honestly it's good. It's healthy competition across the board.
Sure.
All right, so I think we're kind of going to try to close this up. Of course, there are going to be more and more questions coming across the board. I'll plug a couple things again before we officially close this up. So thank you all again for coming to this kind of inaugural Dendrite Day. We do have this Investor Day coming up January 19th. I think it's going to be awesome. You should see more news about that soon. And as Anthony mentioned, right, if you have any questions, you're more than welcome to go to HP's website. He provided the bit.ly link earlier. We can also funnel folks to them through our website, which is dendrite.com/UBM. And if there's any questions for us, please don't hesitate to reach out, whether you're a machine vendor, a software vendor, an advanced user, or just curious. We're more than happy to discuss, and we're always willing and open to listen to feedback and advice. So again, thank you for your time today, and hope to see you at this Investor Day coming up soon.